Hi everyone, thank you for coming to my talk about putting sloths on the map. Any Ice Age fans in the house? This is something that Sid says. He says, I'm putting sloths on the map. But anyway, I'm going to tell you about our journey towards doing destructive testing at Indeed using a tool that we built. I'm Preetha and I'm a software engineer working on site reliability. My background has been in distributed systems, so I've previously worked on Indeed's search indexes and our recommendation engine before joining site reliability. I help people get jobs. You'll see a bunch of us wearing these t-shirts. This is our mission. Indeed's mission is to help job seekers around the world find what they're looking for. We have sites in 60 different countries, 30 languages, and we get about 200 million unique visitors per month. I'm sure you're tired of hearing the word microservices, but I'm going to say it for a few more slides. But anyway, like many other organizations that are out here at SRECon, we also transformed ourselves over the past few years from having very few teams and a few monoliths to building lots and lots of microservices. While we were doing this transformation, we had this perception of what microservices architecture was going to look like. It was going to be awesome with like well-defined service boundaries and simple architecture diagrams that you could keep in your head so that when you get a page in the middle of the night, you know exactly where to go and find the problem. But the reality doesn't look like that. The reality looks more like this, where everybody picks their favorite stack, whether it's Mongo or Elasticsearch or MySQL, to implement their microservice. You've got transitive dependencies between these microservices. And so, and we're also deploying them all the time. So these things are changing all the time because we're releasing software to production multiple times per day because we want to get our ideas in front of users as quickly as we can. The failures in these type of architectures get very unpredictable. So for example, if the link between these two microservices is having a problem, like one microservice is having trouble reaching the other, that might manifest as a user complaining against using an application that's like 2 levels up the stack, saying, I don't know what's wrong. I'm able to edit my job, but I'm not able to change the salary or something like that. And so that becomes very challenging as site reliability engineers when you're trying to support and debug these types of failures. We really wanted a way to reproduce these types of failures in controlled environments so that we could learn how our systems are behaving and improve them over time. While we were doing this, our operational complexity was also growing. In order to serve a global audience of job seekers, we have to be in several data centers. So we're in 8 data centers around the world. It's a very heterogeneous environment. Our software, some of our software runs in VMs. It's mostly old stuff. And then we've got some things that have very specialized requirements, so they run on physical machines. More recently, over the past couple of years, we've heavily invested in moving all of our stack to Apache Mesos. So Apache Mesos helps us orchestrate different processes in our environment. There's also a variety of backends. I wish I could tell everybody, like, hey, you get to pick one data store, MySQL. Just write all of your applications using MySQL as the backend. We don't have that option. People choose what's best to solve the problem that they're working on. So we've got MySQL, Mongo, Memcache, Redis, RabbitMQ, Elasticsearch. Each brings in its own set of failures that you have to learn and understand. We were also hiring a lot. So just look at how many engineers we've hired since 2012. And that's great because that means we have more people to work on helping people get jobs. But not every graph that goes up and to the right is cool. We've also increased the number of incidents. And so there's actually 2 lines in this graph. The red line is total outages. We do have a few of those. Like we had one in Q4 2016, the Dynec DNS outage that affected lots of other Dynec customers, including us. The blue line is incidents where there was some amount of visible user impact, and even that is growing up and to the right. Except in Q4 2016, you do see a drop. Does this mean that I get to pop out the champagne and say that we've solved all our reliability problems? What do you think? No, it's the holiday season. So that's what it is. So the best way to really ensure that your software is reliable is to not do releases. But I'm pretty sure my management is not going to say okay for that. So we do have to release and still ensure reliability. So as a company and as an engineering organization, we really wanted to get ahead of these types of incidents. And we wanted a systematic way to verify the resilience of all of our systems. And this was kind of the place that we were starting from. So just look at this toddler. instead of giving the pinata a good solid whack, he's just hugging it gently. So this is what it's like testing your own code. And I do this too. I'm a developer. I don't think I want to put it through the test. Even if we had some kind of mandates for unit test coverage, we could say that, you don't get to release your software to production unless you get 99% test coverage or something like that. That's still not enough because it only lets you verify one silo and not how it integrates with everything else around you. So we wanted to bring the same rigor that we had when it comes to verifying product features. You take so much. We put a lot of effort into verifying product features. For example, if we were making a small update to our mobile site for employers to post jobs, we would test it in different browsers and different devices and so on. Quick show of hands, when was the last time, or a quick show of hands if you've ever written tests for monitoring code or health check code? Anybody? Oh, there's quite a few, so I'm in the right place. I think everybody thinks similar to us. But yeah, it's not very common. We don't really think about what your monitoring code should do or how the health check should work or how graceful degradation should work the same way that we do for product features. And that's where destructive testing really helps you. Sometimes you've got to blow things up and see what breaks. And we were definitely inspired by all the great leadership that Netflix has shown in this space with their Chaos Monkey tool. They've published a bunch of blog posts about failure injection testing and so on. So definitely inspired by what they were doing and trying to bring the same kind of methodology to Indeed. There were several challenges that we had in bringing destructive testing to Indeed's environment as well. So the main thing is that the same hosts usually run multiple services. This is true both for VMs and for Mesos. It's also a very heterogeneous environment. We do use AWS, but that's not the only thing we use. We have different providers in different regions around the world, and we have thousands of combinations of service dependencies that could go wrong. So we first started out writing some goals. What exactly were we even looking for from a destructive testing system? Security was pretty important to us. We realized that in order to build a good chaos tool, you have to have some amount of privilege escalation. But that didn't mean root access. We didn't want to give root access to everybody to do chaos. It needed to be idempotent, so doing multiple calls should not have adverse side effects that cause things to be hard to debug, because then there'll be complaints that, oh, the SRE team built something and now I'm not able to debug what's going on my service. We wanted to measure who's using it by logging so that we can improve it over time. We needed it to be resilient against crashes or restarts. Again, it would be pretty ironic if we built a tool to ensure that systems are resilient and that itself was not resilient. So this was a pretty important goal. Isolation was another important goal. We have a lot of shared services, and so we wanted a way to test one application's interaction with the service without affecting anybody else that's using that service. We considered some solutions. We definitely looked at Chaos Monkey. It would have been quite an expensive rewrite, but we could have kind of forked Chaos Monkey and made it work for our environment instead of AWS. But that would have been pretty expensive. Also, with Chaos Monkey, you can achieve isolation as long as you implement one IP per app. That means that every application that exposes a port for outbound traffic would have to get its own unique IP address. We were very far away from that in reality. We also considered ToxyProxy. Shopify built ToxyProxy, and it's a TCP proxy that sits in front of your application, and you can interact with it through a HTTP, tell it what to do, and so on. It seemed more tailored towards developer environments than for pre-production or QA environments because it requires using a lot of complex configuration files. Also, we would have had to change all of our apps to point to the proxy address instead of the real address. Another limitation for us is that it doesn't play well with service registration. So applications within Indeed's operational environment don't really hard code where their services run. Instead, they ask a service registry, where does this thing run? And when services start up, they register themselves to a service registry. So that would mean somehow keeping two sources of truth, both in ToxyProxy's config files as well as in our service registration system. And isolation was another issue with ToxyProxy. We couldn't, you can't easily, so say you have a shared Redis or a Memcache and you wanted to test one application using it without affecting other clients, there wasn't an easy way to do that with ToxyProxy. So to address all these needs, we built Sloth. In a nutshell, the TLDR for Sloth is that it's network latency injection as a service. Sloth runs on all hosts in all of our staging environments. It monitors for, implements, and reverses network latency rules. Consider this simple, pretty straightforward stack that people might be familiar with. You have a web application, and it talks to a backend service. The backend service itself might be talking to a database. And then the web application additionally also talks to a memcache. Maybe it keeps like the most recently requested items or something in that memcache. We can inject Sloth between the web application and the backend service. We can also inject it between the backend service and the database. And we can inject it between the web application and memcache. You can also go all in on these slots. You can inject them everywhere in every step of the infrastructure. Sloth is definitely implemented with security as one of its primary goals. In order to access it, you do need to provide credentials, whether you're using its API or its UI. Its changes in Sloth are modeled as a state machine with well-defined transitions between states. So this means because it's running in a very chaotic environment where things are going up and down and being restarted, it can always pick up from the last successful state even if it failed in between. It's idempotent, so this is again important when you're dealing with low-level networking concepts in Linux. So it always tries to verify the current state before trying to apply any changes to the system. And most importantly, it's isolated. So since we have lots of shared services, we can test one specific service against a client without affecting any of the other clients that are talking to the same service. The easiest way to use Sloth is through the command line, through an API. So for brevity, I've actually, to try to fit things in the same slide, I didn't include like the authorization aspect of it. But here's how you could add 10 seconds of latency between employer web app and job posting service. These are just two Indeed specific examples. Like the employer web app is something that employers use to post jobs on Indeed, and the job posting service is like a backend service that it depends on. And so through a simple curl command, we can add 10 seconds of latency between these two. There's also a simple UI around it. It doesn't have many bells and whistles, but if you want to do some type of manual destructive testing, you can always go to the UI and add things manually instead of using the REST API. I told you a lot about what Sloth does and what its features are, but not necessarily how it works. So let's dive into that. How exactly does it work? This is the architecture diagram for Sloth in every environment. By environment, I mean something like staging or pre-production or QA and so on. So we have a Sloth controller, and the UI and the REST API work off of the Sloth controller. The controller talks to a service registry. We happen to use Console for that. If you haven't heard of Console, it's a pretty awesome distributed key value store and service discovery tool written by HashiCorp. So that's where all services at Indeed register themselves with hosts and ports and so on. So when you tell the Sloth controller, add 10 seconds of latency between employer web app and job posting service, it knows to look up in the service registry what machines and hosts and IPs those things actually mean. So it takes all that and translates it into a bunch of latency rules that we store in a key value store. Because it was convenient, we ended up using Console's key value store for that, but it's an implementation detail. We could have used any other key value store for that too. And then down below, we have the Sloth agents. So each Sloth agent is running on a machine within that environment. So every machine or every host in that environment gets its own Sloth agent. And the Sloth agent is just this really simple, very lightweight Go daemon, and it's just spinning and checking whether it has any work to do. Whenever it sees any rules that apply to itself, it goes ahead and implements those rules, and then it can also reverse those rules once the test that you're doing is over. At its core, The Sloth agent leverages two Unix tools called TC, or traffic control, and iptables. I had actually heard of iptables before working on this, but I hadn't really come across TC before. But then later, once I figured out what it was and read the man page and so on, I went and talked to a couple of ops people. And so your ops and your sysadmins and network admins are very familiar with TC, but it's not something that developers really have to hear about much. It's a very arcane traffic control tool. It's a set of queuing mechanisms by which packets, TCP packets, are received and transmitted on any Linux-based operating system. And using TC, the important detail to understand is that you can control traffic flow at the TCP packet level. And that's very useful for us because then we don't need to care about whether the service that the application is talking to is a Rabbit or an Elasticsearch or MySQL or Mongo or whatever. We also leverage iptables. Iptables is a user space network administration and firewalling tool. It has a lot of features and functionality, but we limit our use of iptables to marking TCP packets. Think of marking as giving it some sort of unique ID. So you're basically giving a unique ID to the TCP packet that then your TC rule can use to make modifications to how it should flow. This is all a little bit abstract, so I'm going to try to give a quick visual demo of how this all works. So consider this a single machine, and we have some service running on port 12341, and the first Sloth user comes and says that adds a rule saying that they want 500 milliseconds of latency to all traffic originating from port 12341 on this machine to the destination IP 102345. Then a different Sloth user who might be testing their application, which is different, adds a latency of 1 second, but notice that the destination IP is different, even though the source port is the same. And then we have a third latency rule of 5 seconds, but this time the source port is different. It's 11345, but the destination IP matches the first one. So you can have any combination of these on the same machine. Now imagine that these two little boxes are your TCP packets. So the first two TCP packets are colored with an ID that matches the first rule. So they're going to get 500 milliseconds of latency. Then we get a blue one, and that's going to get 1 second of latency. And then we see a green one, and that's going to get 5 seconds of latency. And this can go on. Now the gray TCP packets are those that don't have any ID associated with them. So they're not marked in any way, and they just flow like normal with no latency added to them. So this is all happening simultaneously on the same machine. We couldn't simply add a bunch of shell scripts around TC and iptables and call it a day. The main challenge there is both of these tools need to run as root, and they need more than one step to accomplish the desired results. So that means that if the machine died or something got killed in between, then it can lead to a very inconsistent state and hard to understand networking behavior on that box. So in order to get around that, we don't give root access to Sloth. We actually run Sloth as its own user, and we use the sudoers file. So if you're not familiar with the sudoers file, it's a way to basically control and whitelist exactly what any user who can run as root using sudo, what can they actually do. So in the sudoers file, we lock down exactly what Sloth is allowed to do. It's only allowed to do things that help it do its job of introducing network latency. It can't do everything that root does. The only way to tell Sloth what to do is through the controller layer, which has access control. So you have to give it credentials in order to make it add latency. I want to describe, so we've put Sloth in place for a while now. It's been a few months, and I want to talk about some problems that we've identified since we've started doing destructive testing using Sloth. So the first one is what I'm labeling as latency amplification, for lack of a better word. This is a screenshot of Marvin. It's a tool that we built on top of Mesos for developers at Indeed to look at all the various daemons that they have running in the Mesos environment. The important detail here is when we first wrote this tool, only a few things were running in Mesos, and so in our infinite wisdom, every row was implemented as a separate database call. And then over time, lots and lots of things, hundreds of things started running in Mesos. So we did a simple test where using Sloth, we added 1 second of latency between this application and the database. And because every row would basically take 1 second to render, that app became completely unusable. But there was another more serious problem, which is that the health check never failed. So the health check for that app was doing a select one query against the database, and it had a 2-second timeout. So it was saying, yeah, I'm green because it returned in 1 second, but the app was basically unusable. So had this happened in production, for an internal app, like taking 1 second of latency between the app and the database is actually okay. But this would have basically made every developer in the company be blocked because they wouldn't be able to look at what's going on on Marvin. And more importantly, if once somebody tells an SRE something's wrong, I can't get to this thing, the first thing they would do is go look at the health check page, and that would just say green. So it would make root cause investigations very difficult. A different, subtly different but related problem that we've seen using Sloth is when health checks don't fail fast. So we've seen this both in external health checks like in Elasticsearch, as well as in our own code, like code that we've written, where we introduce latency using Sloth between an application and a backend service, and the health check doesn't fail, but it doesn't pass either. It just takes a really long time to load because the health check itself doesn't have proper timeouts when it's trying to establish a connection to the backend service. So again, this would make root cause investigations harder because users are going to notice that something is wrong, and they'll come and tell you, but you can't. When you go and see the health check page, the health check page doesn't load, so then you don't exactly know what's going on. You just know that users are complaining that something's not working. So that's an important problem that we caught using Sloth. This can also make traffic failover patterns to break. So again, if you're using some type of load balancer that's pointing to a health check page, and it uses the health check page return value to decide to route traffic to a healthier instance, ideally you want that health check page to fail fast. Otherwise, you also have to learn about what timeout your load balancer is using to ping your health check page, and that can cause some hard to understand debugging and traffic flow behavior. We've also started using Sloth as a verification tool. So we had to implement a complex set of code changes that involved touching a lot of different code paths, where previously it was using a single data source, and now we had a fallback data source. So the code change was, if this master data source is not available, then fall back to the slave. And we used Sloth to basically verify that this change was working as expected, because we had to touch a lot of different places. So we made sure that we would add latency between the application and the master data source using Sloth and verify that it correctly fell back to the slave. We've also started a new practice recently called Destructive Testing Fridays. This was inspired by a blog post that I saw from PagerDuty, where they talked about doing the same thing. So we're working with one product team right now, but we want to expand it to more teams within Indeed, where we sit together and we use Sloth to blow things up on purpose, and then we see what breaks and file a set of action items for ourselves to go and fix, and then we rinse and repeat. I hope that all of this resonated with the audience. Everything that I'm saying is not just Indeed specific. I can guarantee you that your applications also have these blind spots. It's because we don't necessarily think of them until problems happen in production. So please embrace destructive testing for the win. We are still early in our journey towards destructive testing. We want to, now that the basic architecture is in place, we want to introduce more types of chaos beyond network latency. Another thing that this has exposed is that our service discovery mechanisms were not uniform across the board. So for historic reasons, certain Mongo and MySQL database configuration values were only stored in Puppet and not automatically discovered through console. So we're working on fixing that. And we're also working on adding automated destructive testing in QA and production. So before a release goes out, as part of the sort of smoke test, we would also do a destructive test where if your application depends on certain minor dependencies, like if this dependency is not critical to the application, we should be able to blow it, take it off using Sloth and verify that the application still works as expected. So we're still working on that right now. Thank you so much for listening. I've included some of our resources like our engineering blog and our open source contributions, as well as our jobs page. When I'm not in talks, I'm going to be outside in at our booth, and I'm happy to answer questions. I don't have time right now, but I will also be giving a live demo of Sloth if you want to come with me and break things and see what happens in our booth. So that's all I had. Thank you. Questions?
Hi, thanks for the talk. Does it work with containers like Docker?
Containers like Docker?
Yeah.
Yeah, I mean, I think the difference would be, I haven't tried it yet, but it would be like you would have to, we would run Sloth itself inside of Docker, or run Sloth inside the Docker image around the application, and if so, it should just work.
Okay.
Let's give Preetha one more round of applause.
Thank you.